Hello, everybody.
Hello.
Still got some folks coming in here. All right, so lecture for tonight, we're going to talk about thin-walled pressure vessels, which is a kind of a little subset of the combined loading ideas. Let's find this real quick. Okay, so thin-walled pressure vessels are the first subject of Chapter 8. So we're now into Chapter 8.1. Actually, we were in Chapter 8 last time, but more towards 8.2. So anyway, for everybody to stay current on your rating, looks like Chapter 8's a pretty short chapter. Looks like Chapter 8.1 is thin-walled pressure vessels. And Section 8.2, state of stress caused by combined loading, is what we did last class. So yeah, that's it for Chapter 8. Okay. I do not expect that tonight's lecture is going to take a whole hour and 15 minutes, as disappointing as that may be. But that's going to leave us plenty of time to talk about the midterm, if anybody had any last minute questions for the midterm that we have on Thursday. Okay, so apart from the midterm, because we'll have plenty of time to talk about that, are there any questions that anybody would like to ask before we get started? Okay. Alrighty, so for tonight, get that little guy, that guy, here we go. Okay, so this is talking about what generally to me looks like a big old propane tank, I think is pretty much what we're talking about tonight. So you have some kind of a metal container that is designed to hold in pressurized gas, and the pressurized gas will provide or induce stress into the skin of this tank. So the presented method we're about to do here is valid for tanks with an inner radius to wall thickness ratio R over T greater than 10. So if I just section through the tank, as long as the inside radius divided by the thickness of the tank is greater than 10, then this will apply. Many times it's much more than that. Again, if any of you have seen propane tanks that are out in the front yard, backyard of folks who live kind of in the rural areas, these are pretty common. Okay, so gas pressure, P, is caused by the internal pressure of the contained gas. Gas pressure is gauge pressure, which is pressure above atmospheric pressure. So, right, you have atmospheric pressure on the outside, you got atmospheric pressure on the inside. If the tank is empty, then you are in total equilibrium. You're in total equilibrium if all you have is just atmospheric pressure inside or out. But if you open this up and pump it full of any gas, Mustafa, yeah, this applies for any gas. You pump it full of any gas, including air. This could be a compressor tank. right? That stores your compressed air. Then once you pump the gas inside, it has a net outward pressure on the inside of the skin that is above and beyond what is equalized by the pressure outside of the skin. So if we consider a pressure cylinder, so I spent like a whole afternoon making these little sketches, hopefully they read. To create a plane AA, we're going to create a plane AA that's going to slice transverse to our tank. So here's the tank, here's my big guillotine blade, and this is the outside circumference of the tank. If I cut another plane BB, close but not on the same plane, then I have this ring now that is from the outside skin. And finally, if I make another cut longitudinally, then what I'm left with is this little semicircular ring that looks like this. Okay, so I have a half section of a tank wall. The thickness of the ring is the thickness of the skin of the tank, or T, and the width doesn't really matter too much because pressure is pounds per square inch, so every inch gets its equivalent pressure. If I add in a coordinate system, so I call this X, up is Z, longitudinal is Y, then pressure P is equal in all directions because it's a gas. Looking at only the X component of P, we can draw a free body diagram. So here's my isometric. My width of the cut is dy, and looking at it from the end here, I've got the horizontal component of my gas pressure. Of course, the gas pressure has a vertical component, it has a longitudinal component, it has a component in every direction, really. But just isolating the horizontal component, because all the vertical components are going to cancel each other out, right? So, but the horizontal components are not canceled out by anything. They are resisted by this tensile stress, sigma 1, in the horizontal portion of the tank. Does this read for everybody?
Yes.
Okay. So we can draw, we can sum our forces in the X direction based on this. So if I sum my forces in the X equal to 0, then what I have is I have two sections of the tank that are resisting the total force of the gas, top and bottom. So I have 2 times, I have sigma 1, which is the tensile stress in the X direction, and it's equal. Sigma 1 is equal at top or bottom, of course, by equilibrium. And then stress times the thickness times the width gives me a force. So 2 times sigma 1 times T times dy is the total resisting force to the lift. The loaded force, if you will, is P, horizontal component of P, times a vertical distance of 2 times R, because our radius is half of this, so 2 times R, and then times a width dy. That gives me my total horizontal force to the right, resisted by my horizontal force to the left. This equals 0. So a lot of this cancels out, the dy's cancel out, and I'm left with sigma 1, the tensile stress in the skin, is equal to P times R over T. And now if I look in the longitudinal direction, then this is a ring. That's the same ring that we had before. And only now the pressure is applied over this whole circle, is the pressure pushing in. And the resistance is the longitudinal stress in the skin that is intense tension going the other direction. So sum the forces into y equal to 0. I have as my resistance my sigma 2, which is different than sigma 1, by the way. Sigma 2 times the circumference of the ring, 2 pi r, times the thickness of the ring is T. So that's my total resisting force, minus P times this total area, which is pi r squared. That equals 0. So I can sum for theta 2, sigma 2. Sigma 2 is equal to P r over 2T. Okay, any questions so far? So sigma 1, sigma 2 are tensile stresses. P is the internal gauge pressure, R is the inner radius, and T is the wall thickness, as I said before. Could you ever have your sigmas be compression? Could you have a compressive stress? What do you think?
If we
In like a vacuum, would it be yeah? I suppose.
If you had a vacuum outside or inside?
Like if the inside was like a vacuum.
Yes, absolutely. Then you would have a compressive stress. Yep. Or actually what would happen is P would be negative, right? So yeah, absolutely. The other way I was thinking is, has anybody seen the submarine that took a couple divers down to the very bottom of the Marianas Trench? That submarine was, I don't know if I can draw it or not. It was like a top piece. It was kind of like a cylinder. And this top piece, which was a cylinder, had like packets of lead, and they filled it with gasoline, of all things. Any ideas why they filled it with gasoline?
Yes,
Sinks?
because gas is denser than water. I don't know. I was just making a guess.
Well, that's actually a good guess, except that gasoline is lighter than water. See, but gasoline, like a fluid, doesn't compress. So they filled this part of it full of gasoline so that all the enormous pressure of the water would not crush this whole thing like a beer can, because the gasoline would resist that crushing force because it's a fluid, non-compressible. But gasoline is less dense than water. So if you dump all the lead, this thing will float back to the surface. That's why. So, but the divers can't exactly swim and live very long in gasoline. So then attached to this thing is a steel ball. It was a perfect sphere, a steel ball, and I think they gave them 1 or 2 little glass windows. And the divers sat inside the steel ball. And so why did they do that? Because the divers have to be in a air or oxygen environment. Clearly, it takes like 4 hours for this thing to get to the bottom of the ocean, and I don't know, 4 or 5, 6 hours to get back up. So they're not going to hold their breath that whole time. So they're sitting in here in this little sphere of solid steel with 2 little windows in it, maybe 1 window. And so all that pressure on the outside is trying to crush this thing in, but on the inside, all you have is air, which doesn't resist compression. So this would be an example of this scenario in reverse, where it puts huge amounts of compressive stresses on that steel. And I understand the steel ball was something like 6 inches thick, something like that. It was pretty extreme. Anybody know how deep it went? Seeing if there's any other engineering nerds out there like me. Nobody? No clue?
Didn't it go like 2,000 like kilometers or something?
Not that far. Maybe like, no, 2,000 meters wouldn't get you there. No, it was 36,000 feet under the sea, which would be tremendous, tremendous pressure. Okay, moving on. Okay, so we're just talking about a sphere. If you had a spherical vessel, then what happens is sigma 2 is the only stress you have, because there is no point that's not a longitudinal stress, because every which way you cut it, it's always the same shape for a sphere. So sigma 2 is equal to the PR over 2T, and there is no sigma 1 for a sphere. Stress is equal to sigma 2, same in all directions. So that's why the sphere is actually the most efficient shape for pressurized gas. Whether you're containing the gas or you're sitting inside the sphere trying to keep the water out, either way, the sphere is the perfect shape to minimize those stresses. Any questions on that? Okay. Let's do an example then. So I have a tank for an air compressor. It is subject to an internal pressure of 90 psi. And actually I have one of these at home, so I kind of measured it, and just to see if I was in the ballpark or not. If the inner diameter of the tank is 22 inches and the wall thickness is 1/4 inch, determine the transverse and longitudinal stress in the tank wall. Okay, so inner diameter is 22, that means the radius is 11. The thickness of the wall is 1/4 inch. Therefore, R over T is equal to 11 over 1/4 is 44, which is much greater than 10. So the procedure applies just fine. Sigma 1 then is going to equal PR over T, which is 90 psi times 11 over 1/4, gives you 3,960 psi. Do I have a question? Okay. Daniel, do you have a question, or did you forget to mute?
Oh, no, I'm good. Sorry, I was hit the space bar.
Okay, no problem. Transverse stress, sigma 2 is equal to PR over 2T. And so I got 90 psi times 11 over 2 times 1/4. So sigma 2 is 1980 psi, which is kind of interesting, right? That the internal gas pressure is the same. Obviously, anywhere inside that tank, you have the same pressure in all directions. But sigma 1 is your stress. Here, I can draw some arrows. Sigma 1 stress is putting the steel in tension like this. Sigma 2 stress is putting the steel in tension like that. And sigma 2 stress is half of sigma 1 stress, which is why if you've ever seen a ruptured pipe or a ruptured tank, they always seem to rupture this way. Isn't that interesting? You never see them rupture lengthwise. Okay, and so that's the longitudinal stress there. Combining, oh, okay, so this is the last topic for today. I told you this guy, this one's really short, especially if nobody has any questions, this one gets really short. Combining shear stress is just an add-on topic that didn't really seem to fit in anywhere else. So if I have a cylindrical bar, that this is not the cylinder air tank anymore, just a cylinder bar, and I have shear in the Y, I have shear in the X, and I have a torsion upon this bar. All three of these loads create shear stress. Shear stress can have components from shear in the X direction, shear in the Y direction, or you can have shear induced from torsion. Remember the torsional equation where shear tau is equal to TC over J. So torsion causes shear, shear causes shear. The shearing stress from the Vx, the shear in the X direction, looks like this. And the shearing stress theoretically is equal in magnitude across the entire area. So all these little arrows are the same size across the entire gross area of that bar. Likewise, in the Y direction, the shear stress is equal across the entire bar in the Y direction. However, due to the torsional stress, remember when we learned about this, the torsional stress is greatest at the greatest distance from the center of the bar. At the center of the bar, your stress is equal to 0 because C is equal to 0. At the furthest extent of the radius, C is at its maximum. So that stress is a variable stress, and it changes direction as you go around. So this stress is to the left at the bottom of the bar, but it would be to the right at the top of the bar. Okay, everybody see this? Any problems with this illustration? Okay. So shear along different axes can be combined using superposition. So that means that the shear can be the component of the shear in the X direction squared plus the component of the shear in the Y direction. So this is the square root of the sum of the squares. And that is it. So even if you have shearing stress due to torsion, which is tau, if you want to know the total shear at the bottom of the bar, you would add Vx to tau, but if there's any Vy, then you would add them together in this fashion here. Likewise, at the top of the bar, tau would be opposite to Vx, so it would be Vx minus tau squared plus Vy squared, take the square root. Okay, does that make sense?
Can we do an example on this?
Sure. How would I do an example of this? Let's see. If I do that, and let's see. Let's see, how do we do this? If C equals to 1. Okay, so let's say this is a 1-inch diameter. So the area is second pi times 0.5 squared, 0.785 inches squared. J is equal to, oh gosh, I forgot what that was equal to. Pi r pi c squared. I think I want to make this 2 inches, don't I?
I think it's c to the fourth, I'm pretty sure.
Yeah, it's pi half c to the fourth.
C to the fourth, not R to the fourth. See, this is great. This is going to go right into our review for the midterm.
Yeah, it's c to the fourth.
Over pi squared. Or pi, no, c to the fourth over pi over
Half.
2.
Okay.
All right,
Pi over 2 c to the fourth.
pi
Which-
over 2,
0.09817.
1 to the fourth.
Oh, did you? Oh,
Yeah, I was trying to make it simple.
did you 1/2?
So that's 1.57, right?
No, I mean,
Isn't c
is 1/2.
yeah, because if the diameter is 1 inch, I think c is half the diameter, right?
Okay,
The radial distance away from the center, right?
okay, sounds good. So second pi over 2 times
Oh.
0.5 to the fourth. Zero 0.0982. C equals 0.5. Okay. Does everybody agree?
Yes.
All right. So, okay. This is for your guys' entertainment. Somebody give me a shearing load in the X direction.
10.
10 gigafloppies,
MPa. Oh, kips.
10 kips. Okay. Somebody else give me a load in the Y direction.
2.
2. I like it. And lastly, somebody give me a torque.
400.
400?
Okay, somebody else go.
400? You're going to blow it up.
25.
20. All right, 25. I'll do 25. All right. We'll call it kip inches. And let's see, we'll call that positive. So it's actually going the opposite direction as this. Okay. So now for the example. So at the bottom of the bar, Vx is going this way. Vy is going this way. And the torsion is actually in the opposite direction. Okay, so this is tau x, tau y, and this is tau from torsion. Okay.
Is the torsion straight or counterclockwise, you mean?
I was taking it positive, so I took my thumb out from the face of the bar and curled my fingers. So it's actually the opposite of what I drew here. Okay, so at the bottom, I don't have a thing for tau, so I'll just go Tx is equal to, and we have 10 kips over 0.785 equals 12.74 KSI. Okay, and remember to, I don't want that. Get out of there. I can't go back. Oh no. So remember to always include your units. 10 kips, this is 0.785 inches squared, equals 12.74 KSI. And half of getting these problems correctly is just making sure you got all your units properly. So Ty is equal to 2 kips divided by 0.785 inches squared equals 2.55 KSI. And then tau from torsion is equal to 25 kip inch times C is 0.5 inches divided by J is 0.0982 inches to the 4th equals who said 400 again?
Me.
So scaling it down to 25, I still got 127 KSI, which is right at the limit of the strongest steel bolts that you would find. Okay, so therefore, V is equal to, and I'm going to do it like this, square root of, now Vx is going to be 12.74 minus 127.29 squared plus 2.55 KSI, and enclose that, and that equals 12.74 minus 127.29 squared plus 2.55 squared to the 0.5, and we get 114.6 KSI. Where'd it go? You gotta be kidding. What is going on here? Okay, we're having a meltdown.
So, Professor, that V will be the shear at the bottom?
Yes, that's what I was trying to get to.
Oh.
I'm trying. Okay, so you lost this, but what I got was 114.6 KSI. So because the torsion is so much higher than these two, it's actually the opposite scale here, right? The torsion was 127 KSI, this was 12, this is 3, basically. So what you're gonna get is that the torsional is way off, like way off this way, and then it's bent up just slightly by the vertical component of the shear. So that would be the resultant of these three would be that red line. And that's how you use the square root of the sum of the squares. Okay, what did that help? I forgot who asked for an example, but did that help?
Yes, thank you.
What is the final answer? It's 140?
114.6 KSI.
You don't have to square the 2.55?
Yes, you do. Yes, you do. Okay, so what happened here was I wrote the rest of it and it disappeared. Here, let's, V is equal to the square root 12.74 minus 127.29 squared plus 2.55 squared. Okay, does that read? So actually I could do it like this. Put a bracket there, parentheses there, parentheses there. Okay? That, oh, it lost it again. Anyway, does that, can you guys get that?
Yeah.
Okay. Alrighty. It's amazing. I mean, be honest with you guys, it is amazing that when I teach this lecture in the classroom with all of you there, and I'm doing the markers on the dry erase board and all that, what I just presented was a whole hour. I don't know, it's kind of frustrating that I kind of basically blew through it in what, 15 minutes? But it is what it is. So any other questions on this subject matter? This basically concludes chapter 8, by the way. So we're done with chapter 8.
So why do we subtract the 127.29 from the when we do the v of x?
Because this green vector right here represents the v of x, the stress due to the shear load that's going to the left or positive. So this green vector is in the positive x direction. But because the torque is curling around the other way, the torsion is causing a shear stress in the opposite direction. And it's much, much larger. So that's why this one is subtracted from the other. If I was to look at the top of the bar instead of the bottom of the bar, I can show you what that looks like. At the top of the bar, the Vx shear stress is still to the left, but now the torsion would also be to the left, and these two would add together at the top of the bar. Does that help?
Yeah, that helped a lot. Thank you.
Okay, cool.
Professor, one thing just about the way you have it written down in the notes. In our calculation, we use the shear stress, right? So shouldn't the equation be tau instead of V's?
Yes, but the way I wrote it is okay as well. The way that I wrote it was really saying that the shear force is equal to the square root of the sum of the squares of the shear forces. So if you had no torsion, you could take the shear force, which is a vector, combine it with the shear force, which is a vector, and get a resultant shear force. And then tau would be equal to V divided by the area. So you could get the shear force component first, divide by the area and get tau, the shear stress, or you can get tau x, tau y, the shear stresses, and combine them that way as well. The example that I did, I added torsion in there, and you can't just add torsion to your shears because that's in a different direction. So if you're adding torsion, then you'd have to use your shear stresses first.
Okay, cool. So the reason we use shear stress instead of just the shear forces is because of the fact that there's torsion in this example.
Yes.
Otherwise, we could just use the forces.
That's correct.
Okay.
Yes,
Thank you.
yes. And Dima, yes, if the torsion's on the sides, we would subtract add with the y component. Absolutely right. So what you're saying is right here on the side, you would have a vertical component due to torsion and a vertical component due to Vy. Those two would add or subtract depending on their magnitude. And then Vx is in the opposite or the 90-degree direction. So you would combine that using the square root of the sum of the squares. Okay, any other questions on these topics?
So chapter 8 will be only 8.1, 8.2.
Chapter 8.1 and 8.2, we are now finished with. Is that what you were asking, or were you asking if it's on the midterm?
No, I mean, because you said, like you mentioned, this conclude chapter 8. So I'm wondering if we're gonna take like more material in chapter 8 or we stop here.
Well, this is pretty much the whole chapter. Chapter 8.1 was this stuff, the thin wall stuff, And 8.2 is the combined loading, with axial load, mx, and my that we did last lecture. So last lecture was 8.2, and this lecture is 8.1. That's the whole chapter.
Okay, thank you.
Okay. All righty. So that's pretty much it for this subject matter. I will entertain any questions anybody has about the midterm on Thursday.
Are we allowed a full page cheat sheet again?
Yes, yes, you are.
Is it plus the one we have from the first midterm, or just a new?
I would assume a new one because the second midterm doesn't cover the material from the first midterm.
Will it be the same as last time where we start Zoom like 5 minutes earlier and then you give us a code?
Yes.
Okay.
Yep. I'll open up the Zoom like 5 or 10 minutes early. And then when everybody's ready to start, presumably at 5:30, then I will, chat out the code and everybody can get cranking.
And then also, will we have extra time to scan everything?
So the test itself is going to be like last time, where you're going to have 75 minutes to complete the test. And at the end of 75 minutes, the test, if I remember right, the test will close on its own if you don't submit before that. So it's timed that you have 75 minutes for the actual test. And then you have what is reasonable 10 to 20 minutes to scan your stuff and send it into the midterm 2 assignment, where the actual test is midterm 2 test that you fill into text boxes, and then you scan up and submit it to midterm 2, the assignment, which is just going to be set up like a homework assignment.
Okay, thank you.
Okay.
Do you know how many questions are going to be on it?
3. It should be more or less the same effort, if you will, as the first midterm. The first midterm had 3 questions. This one will have 3 questions as well.
I'm forgetting you mentioned that one of the chapters wasn't gonna be on the midterm. Something we did last week, or was that?
Okay. So I got my textbook right here in my lap. So let's go through this real quick. Chapter 4 will be on this test. Okay, chapter 4 was the axial load chapter. And that was a pretty big chapter, by the way. So axial load dealt with St. Venant's principle. And then we talked about elastic deformation of an elastically loaded member, right? You guys remember PL over AE. And then it talked about, or I talked about, producing an axial load diagram so that if you have a axially loaded member that's actually broken into segments, how do you add the deformation from each segment? And that's based on the axial load diagram so that you know exactly what the internal load, axial internal load is in each segment so that you can apply the PL over AE for each segment and then add them all together. We also had in chapter 4 the statically indeterminate axially loaded members. These were the ones where you had a bar of 1 or 2 or whatever different materials wedged between 2 walls. And on that bar, you had some kind of a force applied, and you needed to use these techniques, either the flexibility or the compatibility method, to determine what the reactions were at the wall and what the induced forces are in the bar. again, an axial load diagram. And then the last thing that I recall from chapter 4 was thermal stress. What happens when you raise or lower the temperature on something? And or we had those neat little ones that had the gaps in them. And then you could actually have something that is thermally loaded and has axial loads on them as well. And you need to be able to use your techniques to solve for the reactions and the loads in the actual segments of the actually loaded member. So that was all chapter 4. That was a big chapter. Chapter 5 is a big chapter as well. Chapter 5 is torsion, but at least we had some saving grace that a lot of the principles of chapter 4 repeated themselves in chapter 5. So chapter 5 was talking about torsion, about the shear stress induced by torsion, about the twist or the deformation of a bar induced by torsion. And then we had the indeterminate torsionally loaded members where you again wedged between two supports and you needed to use the flexibility or the compatibility method to find for your reactions and to create a torque load diagram so that you could find the stress or deformation at any given point. So that was all chapter 5. I think we did 2 or 3 lectures on chapter 4, and we did 2 or 3 lectures on chapter 5. If you're having any difficulty recalling this material, I would go back and review those lectures. So definitely chapter 4, definitely chapter 5, and then we did chapter 6. And chapter 6 is probably, I'm flipping to it, but chapter 6 is probably one of the most important chapters of this whole curriculum, of this whole course is chapter 6. Chapter 6 was bending and shear and moment diagrams. We spent a lot of time doing shear and moment diagrams. So that includes, first of all, number 1, you really, really, really need to be sure that you can get the right reactions. Especially for a simply supported beam, you need to be able to get the right reactions. Without the right reactions, all hope is lost because everything else is going to be wrong from that point. So really be sure that you're confident that you can get the right reactions. Then we used a series of cuts to find free body diagrams, and then we found the shear and moment equations as functions of x. Part of that was we all decided, or I told you anyway, that you should always take x from the left-hand support and work your way to the right. You can go from the right and work your way to the left and get the right answer, but you cannot go from the left for part of it and from the right for the rest of it. The answer will be completely wrong. So we talked about that at length, finding the shear and moment diagrams. Oh, and by the way, this just reminded me of something. I want to make sure that I mention this. I have graded, I think, 2 homeworks now that had find the moments and find the shear and moment equations. I think I've graded 2 of these now. A lot of you are catching on and getting, for the most part, the right answer with maybe a typo here or there. But there's a few that, honestly, I'm very confused. I go to grade these, and what I'm looking for is the equation for shear and the equation for moment. And the answer I'm looking for may be like for shear minus 3x, and for moment minus 3x squared, or minus 1.5x squared plus 20 or something. That's what I'm looking for. I'm seeing answers that are like minus 3 plus RA. or for the moment, minus 3x plus RAX or something like that. I'm very confused. Why are you giving me RA as a variable and not using the actual reactions? And I'm not expecting an answer because I don't want to single anybody out. But if you have in your shear and moment equation an answer that has your reaction as RA or RBY or anything that's in the variable form, that is completely wrong. I can't even grade that, it's so wrong. You have to use the reactions that you found from finding your reactions. Don't keep them as a variable. The other point, most of you are catching this, most of you are doing well with this, but do not leave those equations not simplified. Do not give me an answer that's like 2 parentheses 3x plus 4 close parentheses times parentheses 3x or something. No, you give me the simplified polynomial. Such and such x squared minus such and such x plus such and such. Does that make sense to everybody?
Yep.
Yeah.
Okay. Because I want to be clear that if I simply don't have time to finish the math for 30 students. There's no way I can possibly go through and check that your polynomial fractional answer, if you had completed the problem, was actually the right answer. There's not enough time in a whole weekend to do that. So points will be lost if you do not simplify. I want to make sure I'm clear about that. Moving on, we then went to the graphical method of finding shear and moment diagrams. And the graphical method included some theory. The theory was very important. The theory is that, you've heard this 1,000 times by now, but the change in the moment diagram from A to B is equal to the area of the shear diagram from A to B. The change in the shear diagram from A to B is equal to the area of the loading diagram from A to B. So each one is an integral of the one before. And likewise, the slope of the moment diagram is equal to the magnitude of the shear diagram. Slope of the shear diagram is equal to the magnitude of the loading diagram. So we covered that at length as well. And I'm thinking that's pretty much it for the midterm. We are not doing chapter 7 stuff.
What about 6.4?
6.4. All right. All right. What was 6.4? Oh, flexural theory. Thank you. Yes, yes, yes. Flexural theory is on there, or could be on there. It might be on there. The flexural formula where stress is equal to minus my over I. That may be on there. Thank you. I forgot about that. But what I definitely am sure about is that 6.5 will not be on there. 6.5 was biaxial bending. That's not going to be on there. And we're not doing any of the rest of the stuff of chapter 6. Okay, chapter 7 is where we got into the shear formula. That's not going to be on this exam. So the shear formula was the VQ over IB. And you will not see that on this test. And chapter 8 is what we just did with the thin wall and with the combined loading. So chapter 8 will not be on this test at all. Okay, that makes sense to everybody?
So for sure, there's a moment and shear diagram, and then you're kind of undecided if you're gonna put the flexure formula, right?
Yeah, I'll go with that. Yes.
Okay.
Yes.
Okay. Thank you.
So, but for sure, what is really important to this course is chapter 4. I'm not going to tell you what exactly in chapter 4, but chapter 4. chapter 5 and the shear and moment diagrams of chapter 6 is really the focal point. Just as a reminder, make sure you have a working webcam. I need to be able to see everybody as we're taking this test. And be sure that not only are you not on your cell phone, not only are you not texting anybody, unless it's me, then I don't even want to see a cell phone. So make sure there is no laptop, iPod, iPad, iPhone, anything within your arm's reach for test security. If you have an iWatch, I don't even know what those are, so don't wear it. Keep it somewhere else for the test. Does that make common sense? Make sense? Well, just lost somebody. Guess they didn't like the iWatch thing. Any other questions?
Professor, for shear stress due to torsion,
Yes.
does that have significant positive and negative values? Because for one of the homework questions, I asked for max shear stress in two parts of a member, and they're of different materials. And one of them, so I made a torsion diagram, and on the torsion diagram, in one of them, it was a positive torsion. The other one was negative torsion, constant in both ends.
Mhm.
And
Mhm.
the magnitude that I got for each answer was correct, but since the second part of the member was negative, I put it as a negative shear stress, but it was marked wrong on the homework. So, but it was the same magnitude.
Okay. All right. Without admitting guilt on the homework, for the purposes of the test, the absolute magnitude of shear stress is not all that important to me because as you can, oh, I'm not sharing my screen anymore, I guess, but from the shear diagram, the shear stress diagram of a bar in torsion, it totally depends on where you are around the circle as to the direction of the shear stress. So I'm not overly concerned about the positive or negative value of the shear stress, but I'm really straining to emphasize my words because I want to make sure everybody hears me that the actual torsion can and will be positive or negative. And the torsion being positive or negative is very important. That has a very definite meaning to a positive or negative torsion. If you're asked to do a torque diagram, you better have the right positive torque, negative torque on the diagram because a positive torsion, if you stick your thumb out and curl your fingers, is very different than a negative torsion. And what it really changes is the direction of your reactions, but it also changes the direction of the twist. Is it twisting clockwise or is it twisting counterclockwise? And those are important. And those have real physical meaning. Whereas the shear stress due to torsion is a little harder to define because you have to be more specific about exactly where on the surface or inside the bar are we looking for that shear stress. Does that make sense?
Yes, yes, absolutely. And then another separate concept I want to go over is where's the neutral axis in a section of a member? Because it's not always necessarily through the center of it, right? But wait, no, it is through the center of gravity of the cross section, right?
Okay. If you only have a bending moment in one direction, then the neutral axis is going to be, well, it's going to be about the same axis that the moment is about. So the way that we've drawn X is to the left and right, Y is up and down. If you have a moment about the X axis, then the neutral axis will be through the center of gravity and it will be parallel to the X axis. If you only have a moment about the Y axis, then the neutral axis will be parallel to the Y axis and through the center of gravity of the Y axis. If you have biaxial bending, you have mx and my, then the neutral axis will still be through the center of gravity, but it will be at some skewed angle. And you have to go to those notes to find the equation that tells you at what angle is it located at. Okay, so in general, the answer to your question is if all you have is bending, then the neutral axis will go through the center of gravity. However, if you have an axial load in addition to bending about one or two axes, like we just talked about last lecture, then the neutral axis does not go through the center of gravity.
Okay, but for uniaxial moments, it would be through either the X bar or Y bar, depending on which direction the moment is going, correct?
Yes, that's right.
Okay.
Yep.
Thank you.
Yep. Anybody else? Oh, I will mention, I will have an office hour on Thursday starting at 4:30. So if there's something that you're kicking yourself 10 minutes from now, whoa, darn it, I should have asked, you got one more chance. You can always log into the Zoom meeting at 4:30 and I will be there to entertain you for at least until about 5:15. Then I'll need to get ready for the test. Okay, so if no other questions, I'll go ahead and end this meeting. And I will see you all on Thursday.
Thanks, Professor.
Good night, Professor.
Welcome. Thank you.
Professor.